Hello everyone, we're starting our third lesson today on functions and function notation. Okay, so we're going to leave as usual our opening problems that we'll be completing in class. So we will move on to the next page, but before we do functions, I would like to at least do one review problem. So let's take a look at finding the domain and range either using set or interval notation. And you should probably know by now that I'm going to be doing both methods so that you are aware of how to do it both ways. Okay, so if I want to use set notation first on this example, so the first thing I'm going to do is I'm going to take a look at where my values of the x's are starting. So I'm looking at the domain first. So with the domain first, I have that it appears that my values of the x are starting at negative infinity, and they're going all the way up to the value of negative 1, but they're not crossing negative 1 because I do have a vertical asymptote here at negative 1. So there's a vertical asymptote at x equaling negative 1, and there appears to be also a vertical asymptote also at x equaling 2. Okay, so if we go by the assumption of what we had talked about in the previous lessons, we said that sometimes it's easier for us to state the domain as what it's not allowed to be, or stating the restriction as opposed to stating what x is allowed to be. So when I take a look from left to right, it appears that my graph is going towards negative infinity. So if you see the arrow that I've placed here, it seems that it's going to negative infinity, and it's going towards negative 1 but never reaching 1. Then it does happen to go between negative 1 and 2, but it never crosses 2 or negative 1, and then it goes to beyond. It goes to beyond 2. So meaning that it goes to positive infinity. So my domain would the best bet would be here to say the set of all x such that x is an element of R, and remember that we said that we didn't have to place x as an element of R. We could just say the set of all x such that, and then place that x is not allowed to be equal to nor negative 1 nor 2. And that would be my domain in set notation. Now if we were to look at the range in this problem, okay, again using set notation, it'll be y is such that y is going to be an element of R, because we do have curves and they're solid lines, therefore all those numbers in between are being included. And I can take a look and see that it would appear that every number vertically seems to work for the values of y except two numbers. So let's see what those two numbers are. Well, for sure, if I look at this, I see that as I'm moving from bottom up, it would seem that I do have negative infinity, okay, going all the way though towards negative 1. Okay, so it seems to be approaching negative 1 but not crossing it. And at the same time, it seems to be going to 0 and then going towards positive infinity. So what that means is that I can say that my values of the y are not allowed to be equal to, and I will say they're not allowed to be equal to 0 or negative 1 or negative 1, 0. But everything else in between will work. Okay, so that would be our set notation. If I was doing this in interval notation, so in an interval notation, setting the domain should be quite simple, in that I will start from, and because it's going from negative infinity, I will go from negative infinity towards negative 1, and I will do a union with, let me make that a little closer. So negative infinity to negative 1, and there will be a union with negative 1 through to 2, but 2 again is not included, and then there will be a union with 2 not included all the way through to infinity. So that would be my domain. My range is going to go from bottom up, it'll go from negative infinity all the way to negative 1, and then there's a jump there so that there'll be a union from 0 through to infinity. Now, what is this telling us? It's telling us that the numbers between negative 1 and 0 are not included in here, as you can see, because those numbers never show up. Okay? So that would take care of that. Alright, so let's move on to the next topic. Well, the next topic is in section 14b, which is functions. So what we discussed before was, we discussed in the previous couple of lessons, we talked about domain and range, and we talked about relations. And we said that relations were just any coordinate. So any coordinate pair is considered a relation. But a function is really it's a subset of a relation. So it's kind of like when we're looking at the real numbers, okay, the set of real numbers, and then we go and start looking at the more specifics of the subsets of the real numbers. The subsets of the real numbers would be the integers, or it could be the rational and irrational numbers, and then the rational numbers break up into the integers, then they break up into the whole numbers, and then the natural numbers, and so forth. So a function really is a relation where every element in the domain, so every value of the x, is going to get mapped to one and only one element in the range. Okay, so what that means is that every value in the domain has to have a value in the range. So let's take a look at what a function then is. If we drew a mapping diagram just as this, and we had seen this already in one of the first couple of lessons. So if I had the domain 10, 12, 14, 16, and 18, and its corresponding range, that meant that the corresponding range was 31, 36, 48, 53, and 65. Now, that is considered a function because every value in the domain maps exactly onto one value in the range. So it's a one-to-one relationship. So one value of the x is bringing me to one value of the y. One value of the x brings me to one value of the y. Now, that is considered a function. So a function is when every value of the x takes us to one value of the y. When I have a value of the x that is taking me to two values of the y, then that is going to be considered a non-function. Okay? So if we take a look at the next set mapping diagram, we've got 10, 12, 14, 16, 18. Notice that 10 to 31 does map on. There's only one value for x taking us to one value of y. But if I look at 12, okay, 12 shows us that it's going to the number 36, but 12 is also going to the number 48. And then the same thing is occurring with 18. 18 goes to the number 65, but it also goes to the number 70. There isn't a one-to-one relationship. So it isn't just one value of x maps onto one value of y. So if I have one value of x that is mapping onto more than one value of y, such as 36 and 48 in this case, okay, then that means that it is not a function. Okay? Alright, so moving on. So one way that we can test to see whether a relation, because everything is a relation in that everything, any ordered pairs, any coordinates are considered relations, but not all coordinates are considered functions. Okay, so keep that in mind. So what we can do is we can do what is called the vertical line test. And what the vertical line test does is it shows us that for every value of x, there can be only one value of y that goes with it. Okay, so if I were to place vertical lines. Let's take a look at the first graph here. Okay? The first graph is showing me that I have a curve. Now, if I were to make a vertical line go through in several points on this graph, I just put a vertical line going through it as such. Okay? What I end up seeing is that for every value of x, I'm only getting one value of y. There it is. For every value of x, so I've placed a value of x here, I've placed a value of x here, here, and here. And for every value of x, I'm only getting one corresponding value of y. Now if I look at the next graph is showing me that if I put various values of vertical lines through the graph, so I'm just going to put vertical lines through here in different points of the graph, I end up seeing that my one vertical line is hitting twice on that same line. I'm hitting it twice here as well, I'm hitting it twice here as well, and I'm hitting it twice here as well. So what that's telling me is that I am not getting a one-to-one relationship. In other words, this is a one-to-many relationship, in that for one value of x, I'm getting more than one value of y occurring. So because, and again, what it says underneath, it's not a function, because a vertical line could cross the graph more than once. Now, I went a little bit ahead here, and what I did was I wrote that if I were to have a horizontal line, so a horizontal line such as y equaling 2, so there's my line y equaling 2, if I perform a vertical line test on the y equals 2 line, which is a horizontal line, then that would be considered a function, because I'm getting a one-to-one relationship. For every x value, I'm yet getting only one corresponding y value. If I were to pick, though, a vertical line, such as x equaling 5, okay, so here's my vertical line x equaling 5, what you would notice is that if you did the vertical line test on that line, every single point on that line would meet with every other point on that line. Okay? So what that means is that it's meeting at every point, and therefore a vertical line is not considered a function. Okay, so basically there are several ways that we can look at this. So if I look at a function, so I can say that a function has a one-to-one relationship. So if I went from 1 to 2 and 2 to 3 or 3 to 4, this would be like having my coordinate pairs 1, 2, 2, 3, and 3, 4. Well, each one of these is going to a different number. Each value of x is going to a different value of y, and therefore it's considered a function. If I had a horizontal line, as I had shown you on the previous slide, okay, I could have 1 and 2, 3 and 2, and 5 and 2. Now, even though they are going to the same value of y, the fact of the matter is that there are different values of x. And the different values of x that take us to the same value of y are considered a many-to-one. And a many-to-one means that it is a function. It's a horizontal line, as I had shown you before. So there's my 1, 2, there's my 3, 2, and there's my 5, 2. It's a horizontal line, and the horizontal line, when I perform the vertical line test on it, shows me that it is a function. Okay? Now, the one where we know that it is not a function is one where I have one value of x that's going to many values of y. So that if I have 2, 0, or 2, 1, or 2, 2, or 2, 3, for example, notice that the same value of x is going to many different values of y. So a one-to-many is not going to be considered a function. Alright, so the question then is here, looking at our graphs, it says, which of these sets of ordered pairs are functions? So if I look at these ordered pairs, okay, So this is one example, and here is a second example. Which of these sets of ordered pairs are considered functions? So we have 5, 5, 4, 4, 3, 3, 2, 2, 1, and 1. Well, my values of the x are 5, 4, 3, 2, 1. My values of the y are 5, 4, 3, 2, 1. And therefore, I can say, yes, I can say that it is a function. Because for every value of x, I'm getting only one value of y. Now, if I take a look at the next one, I've got negative 3 that goes to 4. I've got negative 1 that goes to 6. I've got 0 that goes to 5. I've got 2 that goes to negative 1. And I've got 3 that goes to negative 1. Now, 2 goes to negative 1, and 3 goes to negative 1. That's fine. That's all right. That's going to be a yes. Okay, so 2 takes me to negative 1, and 3 takes me to negative 1. That is a one to many. Or rather, sorry, many to one, apologize. So that's a many to one. And we said from the last slide, a many to one is going to work. It's right down here. So I've got different values of x taking us to the same value of y, and that's acceptable. Okay, now if I look at the next one though, I have the same values of x. It's 4, 4, 4, 4, and 4 that are taking me to different values of y. And that's a one to many. And a one to many is a no. So a one to many tells me that I do not have a function. So this one would be no. So the third one is a no. All right. If we want to try, if we want to look at the next one, so which of these relations are considered functions? Well, again, this is quite simple in that all you have to do is just perform the vertical line test on it. So I could quickly just do the vertical line test at I could just choose several points here on the graph, and I see that it hits only once. So at each point. So it's hitting only once at each point on the graph. So therefore this would be considered a yes, it's a function. If I look at the next one, that will also be considered a function, yes, yes, and yes, because again, each vertical line is hitting the graph only once. And if I look at the third one, well, as you can imagine, the third one is a no, because for every vertical line that I'm making, I am hitting the graph more than once. In this case, I'm hitting it twice. Okay, so then this one, I would have to say no. So this one's a yes, this one's a yes, and the other one is a no. All right. Now, I'm going to do these. I'm going to ask you to do these in the video. You will work these out on your own. And let's look on, well, the only one I might do is part F. Okay, part F I will do for you because part F is a specific function and it is called a step function. So part F is a step function. So if I were to put vertical lines through the step function, okay, so let's put vertical lines, well, I could put a vertical line right here, and I could put a vertical line right through the 2 points in the step function. And I could put another vertical line right there through the 2 points. Okay, and I could put another one over here. Now, what's interesting about this one is that this one will work out. The first one works out definitely because it only hits the graph at 1 point, that one vertical line. The second graph, or the second line, the second vertical line is hitting twice the graph. But because one of them is included, one of those 2 dots is included because it's colored in, but the other one is not included because it's not colored in, then when it's going through, it's only hitting the graph once. And therefore, this is still considered a yes. This is going to be a function. Okay. Now, the next section is exercise 14C, and it's function notation, and this is quite simple. You've already done this, but I'm just going to show you that there are different ways of writing. Up till now, we've looked at y equals x plus something, or y equals 2x plus 5, or y equals. Well, what we're going to be doing now is we're going to be taking a look at several different ways that we can write functions out. So I can write out y equals 3x plus 1. That is considered a form of function notation, how we write out a function. But I could also write y as f of x. equals 3x plus 1. And I could also write it as f maps x onto 3x plus 1. So these are all three different ways of writing the same function. It's just three different types of notation though. So the first one is y equals, the second one is f of x equals, and the third one is f of x the function x maps onto 3x plus 1. Okay, they all mean the same thing. Whether I call something y equals, or whether I say f of x equals, or whether I say f maps x onto, etc., etc., they all mean exactly the same thing. So, having said that, let's take a look at what occurs here. If we have f of x equaling 2x plus 5, it's like as if I were saying if we have y equals 2x plus 5. Now, what does that mean? It simply means that if I were to replace, for example, the value of x with the number 2, so I just picked a random number, okay, I picked 2. If I pick a random number like 2 and I replace it in for x in the function, or in the equation that's given, 2x plus 5, I would get 2 times 2 plus 5, and that gives me 9. So what does that exactly tell me? It tells me that when I substitute in the value for x as being 2, the corresponding value of the y is going to equal 9. So on the graph, when I substitute 2 for x, the y comes out to be 9. So when I replace a value of x into a function, I get the corresponding value of f of x, or y. Remember that f of x is the same thing as saying y. Okay, so f is not the output, but it's the name of the function. What the output is, so I have an input. In the previous page, our input was 2, and our output was 9, f of x. Okay, so f of x is the output, not f. So you should note that f is just a label, and it really could be replaced with any other letter. So when I call it f of x, well, technically it could be g of x, h of x, k of x. I could even call it k of t if I wanted to, depending on what I'm talking about. Okay? So what we want to do is we want to now evaluate functions with function notation. Alright, so what does that mean? Basically, if f is the mapping of x to 5x plus 1, then f of x equals 5x plus 1. So what does that mean? That if I plug in, or if I replace x equals 2, we're really doing f at 2. So all we're saying is that wherever there is an x, we're going to replace it with the number 2. So f at 2 equals 5 times 2 plus 1, which equals 11. So f at 2 equals 11. Now, sometimes we don't want to replace just a number, but we might want to replace an entire expression. Okay, so we don't want a particular numerical value, but maybe we just want to replace x with x plus 2, for example, or x plus 4. So wherever there's an x, I'm just going to replace it with x plus 4. So let's do an example down here. The example I gave down here was, if I have f of x equaling 2x plus 5, and I decide to do f at 3, well, that just means that I'm replacing, for the value of x is being replaced with 3 to get the corresponding value of y, which goes to 2 times 3 plus 5 equals 11. But if I'm replacing x with not just a number, but I'm replacing it with an expression, what that means is that wherever I have x, such as x plus 4 here now, f of x plus 4, wherever I have an x, I'm going to replace it with x plus 4. So if I use f of x again as the example, wherever I have an x, I am now going to replace that with x plus 4, so that I end up getting 2 bracket x plus 4 plus 5, which equals 2x plus 13. Alright, now, if f of x equals 2x plus 12, let's just do another example. If f of x equals 2x plus 12, the question is asking, find f at x plus 3. So again, we replace x with x plus 3 wherever there is an x. So f of x plus 3 is going to equal 2 times x plus 3 plus 12, which, when we simplify, goes to 2x plus 18. And now, if I wanted to do f of x equals 2x squared minus 3x minus 2, and I wanted to figure out or find what f at negative a is, all that means is that wherever there's an x, I will replace it with negative a. So f at negative a is going to equal 2 times negative a squared minus 3 times negative a minus 2, and then we just simplify from there so that we get 2a squared plus 3a minus 2. Alright, the very last question we're going to do, and then we're done, is one last question here, and it says, if r of x is equal to 2x plus 3 over x plus 2, they want you to evaluate r at 0, r at 1, and r at negative 1/2. Okay, so let's do a. Okay, I already have the layer on. Let's turn it on. So if I do a, and I have to evaluate, so I'm going to start doing r at 0. And that equals 2 times 0 minus 3 over 0 plus 2, and that ends up giving me negative 3/2. Alright, if I now do, this is I, if I now do 2i, if I do r at 1, well then this would go to 2 times 1 minus 3 over 1 plus 2. And that goes to 2 minus 3 is negative 1 over 3, which is just negative 1/3. And then my last one would be r at negative 1/2, so we're going to deal with a fraction that's going to be on top of another fraction, so that I will say r at negative 1/2 is equal to 2 times negative 1/2 minus 3 all over negative 1/2 plus 2. And so when I simplify that, well, I can simplify the top by multiplying it, so I get negative 1 minus 3 is divided by negative 1/2 plus 2, so we'll get a common denominator, gives me 1.5. So that'll give me 3 over 2, and so that I get negative 4 over 3 over 2, negative 4 over 3 over 2, which becomes negative 4 times 2/3. And that ends up giving us negative 8 over 3. Alright, that's part A. In part B, what we do is we have to find a value of x where r of x doesn't exist. Now, if you recall, what we said was that r of x, we said that we are not allowed to have a denominator that goes to 0. When something doesn't exist or is undefined, then what we have to do is get our denominator to go to 0. So the number that makes the value of x, or that makes the denominator go to 0 in this case, is going to be the value negative 2. And all I did in order to figure that out was to say that by taking the value of x plus 2 here in the denominator, and I set it equal to 0, because if I set it equal to 0, I can figure out what value of x is making it go to 0. Now, it's obvious if I just have to look at this one, and I know that the answer is negative 2, so it just goes to negative 2. So I know, therefore, I can say the value of x must be x equaling negative 2, so that r of x doesn't exist. So that r of x doesn't exist. Okay. All right. Part C. Part C says, find r at x minus 2. So what that is basically telling us, and place that in simplest form, it's just telling us that wherever there's an x, we're going to replace it with x minus 2. So I'm going to do 2 times x minus 2 over 3, minus 3, minus 3, all divided by x minus 2 plus 2 is going to equal 2x minus 4 minus 3 all over x. So that we get our final answer to go to 2x minus 7 all over x. And we'll just leave our answer as such. Now, for part D, it says to find the value of x if r of x equals negative 5. So what this is telling you is basically this. Since it's r of x is really like saying y, they're just saying if y, so they're basically saying if y equals negative 5, what is x? Saying what is x? Alright, so all I need to do then is I just need to say, well, if my r of x is equal to negative 5, I will say negative 5 equals 2x minus 3 over x plus 2, and I will isolate for x. Now, we learned this just in our last section, isolate for x and solve. So in our last section, I'm just going to move this up so that we will have then negative 5 times x plus 2 is equal to 2x minus 3, and we have negative 5x minus 10 is equal to 2x minus 3. I can say that negative 10 plus 3 is equal to 2x plus 5x, so that negative 7 equals 7x, and x equals negative 1. So that means that in order for me to have a value of y equaling negative 5, or for me to have r of x equaling negative 5, my value of the original x would have to be negative 1. Now I could actually check that by replacing x equals negative 1 back into the original equation, and that should give me my left-hand side equaling my right-hand side. So if I just check that, I could say negative 5 equals 2 times negative 1 minus 3, and that gets divided by negative 1 plus 2, so that I have negative 5 is equal to negative 5 over 1, and there it is, negative 5 equals negative 5, so that my left-hand side does equal my right-hand side. Okay, so your classwork is already posted here, so we will continue this in class. See you next time.